open ocean, vast, silent, and seemingly empty, yet nothing could be further from the truth. Beneath this blue expanse lies the most powerful life support system on Earth, an invisible engine driving oxygen, climate, and life itself. Welcome to the story of the open ocean and its tiniest architects, phytoplankton. In the living Earth system, everything is connected across scales and systems. Within this architecture, the open ocean forms a critical layer, Tier 2 ocean systems, where planetary metabolism unfolds. Here, vast biochemical processes regulate oxygen and control the flow of carbon across the planet. This is not empty space. It is the biochemical heart of Earth. The ocean dominates our planet in scale, in reach, and in influence. It covers most of Earth's surface and represents nearly 95% of the biosphere. Within its depths lies the largest reservoir of carbon on the planet, silently shaping climate over vast timescales. This is Earth's largest living system and its greatest storehouse of carbon. The ocean is Earth's climate regulator, absorbing shock, stabilizing extremes. It takes in nearly a third of human-generated carbon dioxide and captures most of the excess heat trapped in the atmosphere. These vast waters buffer temperature and maintain the delicate balance that makes life possible. Without the ocean, Earth would be far hotter, far harsher, and far less stable. Now, at the heart of this vast ocean lies something almost invisible. Phytoplankton, microscopic, drifting plants suspended in the sunlit surface waters. They harness sunlight, absorb carbon dioxide, and quietly manufacture life-sustaining energy. Individually, they are tiny, almost insignificant, but together they power the planet. Look closer, and an extraordinary diversity begins to emerge. Diatoms encased in glass-like shells, drifting with the currents, dinoflagellates, moving with whip-like tails, glowing in the dark, cyanobacteria, among the oldest life forms on Earth, and coccolithophores, armored with delicate calcium plates, hundreds of thousands of species, each adapted to precise ocean conditions. Together, they form a living mosaic, driving the engine of the ocean. At the core of this living system lies a powerful transformation. Using sunlight, phytoplankton absorb carbon dioxide and convert it into organic matter. In the process, they release oxygen into the ocean and the atmosphere. This simple act, repeated billions of times each day, produces nearly half of the oxygen we breathe, an invisible engine sustaining life across the planet. The scale of this activity is almost unimaginable. Every year, phytoplankton produce around 50 billion tons of organic matter, a level of productivity comparable to all the forests and plants on land combined. Across the vast open ocean, this continuous flow of life fuels ecosystems and drives the global carbon cycle, tiny organisms with planetary scale impact. Phytoplankton live fast and respond instantly to change. They grow rapidly, dividing and multiplying in a matter of days. When conditions are right, sunlight, nutrients, and calm waters, they explode into vast blooms, visible even from space. But their lives are short, fleeting, and dynamic, a constantly shifting system reflecting the pulse of the ocean. Phytoplankton sit at a critical junction between the atmosphere and the ocean. At the surface, carbon dioxide moves from air into water, captured by these microscopic plants and transformed into living matter. From here, carbon begins a journey through the ocean's layers, linking sky to sea and surface to depth, a bridge in the global carbon cycle. This journey continues through a powerful mechanism, the biological carbon pump. First, carbon dioxide is absorbed and converted into living biomass. Then, as phytoplankton die or are consumed, this organic matter begins to sink downward through the ocean's layers, carrying carbon with it from the atmosphere to the deep ocean, a silent conveyor, moving carbon out of the air and into the depths. As this carbon sinks, it enters a mysterious region, the ocean's Twilight Zone. Between 100 and 1,000 meters below the surface, light begins to fade. Here, Much of the sinking organic matter is consumed, broken down, and recycled. Only a fraction continues its descent into the deep ocean. This zone determines the fate of carbon, how much is returned, and how much is stored for centuries. Beyond the Twilight Zone lies the deep ocean, vast, cold, and slow-moving. Here, the remaining carbon settles far below the reach of sunlight. Locked away in deep waters, it can remain for centuries, even thousands of years. Circulation is slow, the return journey even slower. This is long-term carbon storage, a hidden reservoir, stabilizing Earth's climate over deep time. Alongside biology, another process is at work, the solubility pump. In colder regions, surface waters absorb more carbon dioxide from the atmosphere. As these waters cool, they become denser and begin to sink, carrying dissolved carbon deep into the ocean's interior. Over time, this carbon is stored far from the surface, a physical pathway, quietly reinforcing the ocean's role as a carbon sink. At the base of the ocean's living system lies phytoplankton. They are the primary producers, the first link in the marine food web. Consumed by zooplankton, which feeds small fish, which in turn sustain larger predators, from tiny organisms to massive whales. Every level of ocean life depends on this foundation, a vast web of life built on microscopic beginnings. Beyond food, phytoplankton sustain life in another profound way. Through photosynthesis, they release oxygen into the ocean and the air above. Nearly half of the oxygen on Earth originates here in the open ocean. Every second breath we take is linked to these microscopic organisms. The ocean is not just a carbon sink, it is the lungs of the planet. The impact of this system extends far beyond ecology into human survival. Ocean productivity supports fisheries, feeding billions across the world. It sustains livelihoods, drives economies, and underpins what we call the blue economy. From small coastal communities to global supply chains, human life is deeply connected to the health of the ocean, a natural system with global economic consequences. But phytoplankton are not evenly distributed. They thrive where conditions align. Along coastal zones and continental shelves, nutrients are abundant. In upwelling regions, deep, nutrient-rich waters rise to the surface, fueling growth. Near the equator, winds and currents sustain continuous productivity. Where nutrients meet sunlight, life flourishes. Hotspots of activity in an otherwise vast ocean. But much of the ocean tells a different story, one of scarcity. In vast subtropical gyres, waters are warm, stable, and nutrient-poor. Here, mixing is limited and nutrients remain trapped in deeper layers. Phytoplankton struggle to grow, and productivity declines sharply. These regions, often called ocean deserts, reveal the limits of life in the absence of nutrients. Phytoplankton dynamics are not static. They shift with seasons and climate. In higher latitudes, spring and summer bring bursts of growth as light returns and nutrients rise. In other regions, winds and currents drive cycles of abundance and decline. And on a global scale, climate patterns like El Niño reshape ocean productivity, a system in constant motion, responding to the rhythms of Earth's climate. Now, this delicate system is beginning to shift as the ocean warms. Its layers become more stable, a process known as stratification. Warm surface waters sit above colder, denser layers, reducing vertical mixing. Nutrients from the deep no longer reach the sunlit surface in sufficient amounts. The engine begins to weaken as warming reshapes the structure of the ocean. The consequences are already beginning to emerge. With reduced mixing, phytoplankton growth begins to decline across large regions of the ocean. Nutrient-poor zones expand, turning productive waters into biological deserts. Less phytoplankton means less carbon captured from the atmosphere and a weakening of the ocean's natural climate regulation, a subtle shift with global consequences. But imbalance can also move in the opposite direction. When nutrients surge, from runoff or pollution, phytoplankton can grow out of control. These explosive blooms often release toxins harmful to marine life and humans. As they decay, oxygen is depleted, creating vast dead zones, from life-giving organisms to agents of disruption, a system pushed beyond its limits. This is where the system begins to loop back on itself. Fewer phytoplankton means less carbon absorbed from the atmosphere. More carbon in the air drives further warming, and warmer oceans further weaken phytoplankton growth, a reinforcing cycle where a weakening biological pump accelerates climate change itself. Step back and the full picture begins to emerge. From microscopic cells to planetary systems, phytoplankton connect the smallest scales of life to the largest forces shaping Earth. They regulate oxygen, drive the carbon cycle, and sustain ocean ecosystems, invisible to the eye, yet immense in impact. The smallest organisms governing the largest systems. And so, the story comes full circle. The health of the ocean and the stability of our climate are deeply intertwined. Protecting these waters means safeguarding the processes that sustain life on Earth. From unseen phytoplankton to the air we breathe, everything is connected, fragile, and vital. Protect the ocean, and you protect the climate system